Hi, this is Bill Foote, and I'm going to be looking at a portion of week 2 work where we synthesize customer data. And we're going to use some tricks of the trade in this spreadsheet to do so, including a sampling using a Poisson sampler, which has some very interesting properties inside of it. You can see we can pop this around. Build just starting at the end result, and starting from where we end up, which is this synthesized MooseCo data graph over here. You see there's some perturbations in it. The smooth version of this is what we've been building so far, which is limited capacity and endogenization of behavior between predator and prey. The customer base is battling it out, WolfCo versus MooseCo. This is the smooth version. Over here we have the sampled version, and what we will do with the synthesized data is use that to validate our statistical causality models that we are going to end up pulling together and then applying decision criteria against to complete the circle on decision analytics and gain some strategic decision intelligence. Uh, that's the graphs. We started this whole journey with a Vensim model, and this is a sidebar version. This is a screen grab from it. And you can see very similar drawings here. This is called a limit cycle diagram, a phase diagram. Shows the relationship between wolf and moose in this particular case. These pictures are very interesting, and we will talk about those at another time. The inputs to this model are 7. And what we want to do is we want to perturb one of the inputs. Now we can perturb them all. We can also correlate the perturbations, the way in which they literally vibrate against one another. But in this simple spreadsheet that we built, we're just going to move the initial customer number, which originally was 150. We're going to give it a standard deviation of 50, and this intensity level, which in statistical representations of the movement of data is called lambda. It's the intensity of a Poisson distribution. So lambda will indeed be sampled from a normal distribution here. Often we'll use a gamma distribution, but normal's good enough for our demonstration at this point. And we can see that using Poisson INV, the inverse, just like we do with the normal inverse. Love the differences. It's using dot versus underline. We can sample using a random number, a probability, a number between 0 and 1 is what is delivered by the random kernel here, of D. So whatever lambda we pull out of the Gaussian normal curve jar, in this case 161, we then go and ask the question, well, what would that look like if it came out of a Poisson sampling jar? And it's 162 in this particular case. Now we can play around with this a little bit just to fire this. In this case, it's a very low lambda, producing a sample of 66. And we keep working this. 170 gives you the 174 in this particular case. So we can move uh, the synthetic data around a little bit by making the statistics that would stylize that data different. In this case, the mean and standard deviation. Easy to interpret um, as opposed to a gamma, which we can also play around with and get means and standard deviations, but a little bit more textbook here just for um, demonstration purposes. The model itself is the same model that we've been using before. Again, using some wizardry from the text analysis side of a spreadsheet, using left, right, length, all sorts of things to play around with in order to carve out this simple string of A, which stood for auxiliary, customer's initial, which stood at originally 150. From the readout, which is just a simple dump of data from the documentation side from a Vensim model. So the workflow starts with Vensim. No, actually it starts with paper and pencil. And then we move it to Vensim and play around with it, which is the point of the slider bars that we can see here. We play around with it in order to understand the way in which behavior over time and cross-sectional behaviors can possibly mix in this model, and you could use this part to validate that we have enough here to answer the questions that we are posing. We have the inputs again, the model, and then we built a simulation of this with time, again using some a little bit of simple programming. Now these are exactly the model pieces. So if you wanted to know what the flow, F standing for flow, Moose acquisition, we go back to the model. Notice all of the auxiliary variables are together very nicely, and the flow variables are together. And here's the Moose acquisition model, basically. And that model reads, take the Moose acquisition rate, multiply it times Moose availability, whatever that is, that's the next couple of things down, times the level of Moose at that time step. We also have to multiply this times the time step as well, which is not shown in this particular rendering of the data. So we do have to know something about modeling here to get this to work in a spreadsheet. There's the step. And the step is one of the three standing data system inputs. T0 is 0. The step is 0.002 in this case of a month. And the final value will be 24 months. So that's how we're reading this and interpreting it once again. Going through the model. And if we go through the simulation, this model simply picks up previous values of, in this case, Moose and Wolf, as we're flowing through, back to the Vensim, as we're flowing in inputs into the Moose stock, MooseCo really, customers, remember, not Canadian snowshoe hares, and flowing out as customers float out for some reason or other. Okay, so they're out here. And the Moose stock also gets involved in the acquisition for Wolf. And thus we get these concurrent curves here. A lot of things can be modeled this way in interactions, as we've said over and over again. To me, this is the basic model of decisions. these could be two decision states. Build, buy. Okay, how many things you're going to build, how many things you're going to buy, or the money involved in building, the money involved in buying, with inputs and outputs, and all of the rest of the computations are being carried by these A variables as we go through. So we build all of this into the simulation. Wolf acquisition takes two rates, and both G, that's the wolf, and F, that's right. Look it up. There it is. That's the moose. And again, times the time step. That's happening across a very short time step. What's 0.002 of 30 days? Hours. Okay. So that's the model we built, and we also endogenized some of these situations here, interactions with a customer potential market base, which, as you can see, will be declining over time. And then over here, we had the rest of the endogenation exercise, which we've already discussed in a previous video, involving some allocation of wolf and moose coming out of the potential base. Other allocation rules could be posted here. This capacity for both changes over time as well. This thing called availability tends to be constant in this model. That needs some work. So that's the wind-up for what we're doing over here in this sheet, which is the synthetic data sheet. And the synthetic data sheet pulls using index and match, which is a very probably better documented approach to pulling data from various tables without using VLOOKUP or HLOOKUP. Get into some trouble with both V and HLOOKUP. We have to do some extra computations and drivers in order to make that work in this particular case. So we just end up using index, where we're reading using the indirect function, reading anything that's in sMoose. As you can see, what is sMoose? Yeah, it's here somewheres. sMoose is this entire vector of F2 all the way down to F12,002. And we're making all of these integers. Well, we could. We don't have to. I was playing around with that. If, by the way, we did, which is a very interesting thing, just take the integer part, which is a round down type of function inside of Excel, you will get a very, very different range of interactions. Some of it the same shape, but quite a bit more like a step function. But that's neither here nor there. We do the same for wolf. This pulls out, given the month, from sMoose, report from sMoose, the right row for time 1. So that's pretty straightforward. And we check these in the right piece of information for time 24. Now we're doing this because the simulation runs everything on a 0.002 of a month basis. We don't need all of those 12,000 pieces of simulation. We just need 24 of them because we're building a monthly model. Oh, I didn't mention that before. We are building a monthly model. So we need to pull those pieces of data out. The index match does that directly for us. And then this last column will be our result. the Moose synthesized data. Now, I'm just using Moose here. We could also do Wolf and customers very, very easily. That's not a hard thing to do. That's a fairly straightforward thing to do in all of these runs. Now look at the design of the simulation itself here. This is a synthesizers. We did a deterministic simulation in the simulation tab. Here we do a sampled simulation, a statistically run stimulation. Stimulation, yes. And the two things that are driving it are a variable intensity of potential customer. We call this lambda in a Poisson distribution. A review of the Poisson would be helpful here. And it's not that difficult to do. It just basically takes how many zeros or how many ones from customers appearing or not appearing and adds them up. It aggregates them across some frame, time frame or market frame of some sort, maybe by location or whatever it is. But that's a Poisson distribution built on the binomial distribution. And we are sampling from a distribution with a lambda of 170, and the sample will give us 174. Based upon this, this is input to our major simulation, which happens out here. So we sample it, this whole simulation changes, and then our index match over here pulls up what happens in month 1 through month 24. Well, this all continues. As this gets recalculated, it runs, in this case, just 100 times. There we go, 100 times. We normally like these things to run thousands of times. You will see why we don't want to do that in the spreadsheet at this moment, as we're just doing the demonstration. Very clearly why. The runs are just a simple formula over here. The heavy-duty work is happening line by line. As it recalculates this line here, which we will call the interface, you can see its name is the interface, gets copied and pasted over here, which you can see we call the simulation line. Now, it doesn't get actually copied into that line. It gets copied into whatever the next available space line is available. So it's here, then it runs to here, and this 170 is copied here. And then when this recalculates, when the sheet recalculates, it copies this whole line from J down to AI down into this space here, item by item, run by run. So we're basically going to count the runs and use a function called offset to do all of that, which works quite well. But in order to do that, we have to write some code. Let me just show you the code briefly. And that's, you need to have developer in your tab up here. And here is the run synthesizer subroutine. This is becoming old school very, very quickly. We have to declare our variables. We have range variables. We have an integer variable called iRun. R1, R2, and R3 are the ranges. We set application screen updating to false because that just takes even longer to get things done. And we're only going to do 100 runs. Now we can specify the number of runs outside of this by simply developing another, like maybe R4. We set R1 to be the range calculation. You saw, did not see what that is. Let me show you what that is. Calculate means recalculate this. In other words, perform this action just like this. That's a recalculation. Boom. See that? But the recalculate region is that region. So it's basically saying recalculate that region. Actually, you only need to do one of them, but this is a little better from a documentation point of view of what we're trying to do. Recalculate all these numbers. Remember, they're being driven by different versions of lambda, and the sampling from lambda, in this case, a huge number, 247. And by the way, you can see this over here. Very different numbers are being generated, and this phase is extremely interesting in this particular case. With our original work from week 1 and week 2, very different numbers are being generated each time you play with this. Let's see, let me do it again here so you can just see that again. Yeah, see? That's a little bit more normal. Every time it recalculates, it resamples. That's the point, and each sampling is deposited quite naturally here from the inputs. That's the resampling from there. And from here, transpose of D4 through D27. So we're generating Moose data in this particular case. We can generate all of the data, but then we would have to put our machine down and go and do something else for about half an hour. Okay, it's that much data being pushed through a machine like this. This is not the optimal machine to run any of this on, but it is a good way to see how it all comes together. And what you see is what you get here. A little bit easier to see some of the process and the workflow. We can take this as a way to go ahead and then program it in something more serious like C++, plus R, Python, etc. We can just go there directly. Very different kind of thinking here going on as well. But each one of these lines gets copied down here 100 times. And as I promised, here is the way it works. We set the ranges, and for each, and then we add another. We start at 1, we recalculate R1 calculation, recalculate R2 R2 we copy the interface, all that data, and in R3, which is that simulation bar, we use offset of 1, 0. The offset is just run on a row, not a column. So each row, it just goes to the next row, to the next row. So we're at row 1. And it's important to realize that what happens in Excel, row 0 is where simulation is. That's how Excel thinks about it. So row 1 would be the very next row underneath that. And then row 2 would be the 1 and 2 under it and 3 under it and so on. And we're directed to do a paste special of only values. Excel paste values. Now you have to know the syntax for this and look it up on Google, the Ultimate User Manual, anytime, or the Edge, of course. I'm also playing with putting it into a something like simulation called iRun, which is a named variable. See, we're using all named variables here. And we're also doing a status bar. So every time we run this, the status bar, which is the bottom of the screen in Excel. This down here says ready and all these other things. That's called the status bar. So if we run this, and I'm just going to run a couple of iterations of this. The last time I ran it was just 37 iterations. I'm going to run this button, and as you can see, things, oh, we have a type mismatch somewheres. Oh, yes, good thing to show. Yes, I wrote something wrong because I was in another language at the time. All right. You're supposed to put run and I run. Well, if this was Python, you'd use a plus. Here, the concatenation operator is an ampersand, just like in the cells. Well, that's a nice note. And then we'll just save this for posterity and see this. Notice the space between N and the quotes. We're going to need that space. We can also put this here, ampersand. And put a little bit more text there. It's out of 100. So it almost gives us a percentage idea, which is kind of nice. Because it is out of 100. Matter of fact, I could just as easily put percent there as well. But I love rational numbers. And there we go. Okay, now let's see this run. Notice the run stopped at 1. It tried to do 1. Okay. There we go. See what happened down here? Two out of 100. Okay, see how slow it is? Well, why is it so slow? Every time it recalculates, it's recalculating how many variables do we have? How many flow variables? How many stock variables? We have 3 stock variables, 2, 4, 5 flow variables, and several auxiliary variables being recalculated. Well, it's 7, 8, 9, 10, 11, 12, 13. We have 13 variables, 13 columns of 12,000 each being recalculated. Well, that's a lot of recalculations. And then all the rest of the sheets are recalculating as well. We're already up to 8, as you can see, 9%. We have to take 3 breaths, 10%. Okay, quite a bit, quite the amazing thing. Now you can stop all of this action very easily by hitting the escape. See if I can get into here. I can get into if I can get into the developer. Already up to 15, 16. And we can go and take a little coffee break right now and be right back. 17. It's like watching paint dry and grass grow. Yes. And that's okay. That's okay. We have other things to do. So let me pause here. You can refresh yourself with your favorite beverage. Get up, stretch, and see you in a couple of minutes, actually. As you can see, we're at run number 97. Each run takes approximately 5 seconds, so this is well over 8 minutes just to do this very simple, actually insufficient Monte Carlo sampling that I have proposed here. Again, this is a demonstration of what could happen. And the final thing that was produced, I actually like this a little bit better. It doesn't look like this so much. I get some perturbations out of this. Good. Good sampling. I think we're going to keep this one. Yeah, I like this a little better. How did we get that? Well, in the synthetic data, we calculated the medians. In this case, I wanted to calculate the medians of the two parameters as well. I'm going to use that later on to um, formulate something that we'll call a posterior distribution of these parameters as they walk into this very complex model, which is typically like a regression model, but the regression models are so unbelievably standardized to be simple linear models. They often work very well, which is great, but not always very helpful. I just want to make a couple of more points as we go through this exercise. Yes, it takes 8 minutes just to do 100 runs. Typically, we do thousands of runs. And we also do what are called Markov chains, which are thousands and thousands and thousands, and average them up because of the way the Monte Carlo samplings work to get a much cleaner sampling idea of what this data could possibly look like. We haven't even observed anything in the marketplace. And we would use this to help us validate a model, because it's a sampled model. But if the marketplace wasn't Poisson distributed with lambda distributed variates, then, well, we got another problem. We need a different sampling regime. Okay, that's what we call our observational model. All of that is in the next couple of weeks, which we will be getting into even more. Week 3 is Bayesian, what I call the Bayesian interlude, and look forward to you joining us with that. Look, run 100 out of 100. Did a little programming, did a lot of Excel work here. All of this in systemdynamics101.com uses R instead of Excel, which means we can pretty much accelerate things tremendously here with the Monte Carloing. But the same work process is there as is here. And I hope that this was helpful in understanding the mechanics, really, of what we're trying to model. We're observing things in reality. And with those observations, we make stylized representations. We then use mental models. Probability doesn't actually exist, but what does exist, something is represented by probability. Some things happen some of the time, other things happen at another point. Sometimes they happen together. That's what we actually observe. And then we build a model around that. And that's what we have done here. In this case, synthesizing data to validate a model, but also to get the conversation going with a decision maker, especially if we don't have good data yet available. We might get some interesting things there. Anyways, cats are calling. They must be fed. Thank you for your kind attention, and we'll see you in the next round. Take care and keep encouraging each other while it is still today.